today we're going to do a few bell work problems, and then we're going to talk about how we can use scatter plots in a better way using what we call a line of best fit. So first of all, on this scatter plot, we're going to answer a few questions. What is the dependent variable? Well, the dependent variable is the y value, so that's the distance traveled. Then the independent variable is the x values, the stuff listed on the x value, or x line, and that happens to be time. And so how can we look at this and kind of make sense of it? Well, the longer time passes, the more time passes, the farther you can go. It's like if you're riding on your bike or walking or driving a car. So that's the relationship there. All right, now next we're going to look at this equation. This is a linear equation that we saw quite a bit earlier in the year. And it's got x's and y's and a constant. We're going to write it in y equals mx plus b form, where m is the slope and b is the y-intercept. And we practiced this quite a bit, so hopefully it's not totally new to you. But first of all, we're going to give ourselves a Great Wall of China here, and we're going to move x to the other side by subtracting x on both sides. And when we did these, we showed you how you could actually just move it and change its sign, but we'll try and go slow here. So we're going to have 4y equals negative 1x, and we're going to write the x first because that's how slope-intercept form likes to have the equation organized. Next, we're just going to divide everything by 4. Hopefully this is looking somewhat familiar. And then when we're done, we can just write the equation y equals negative 1/4 x minus 2. And that's what we call a slope-intercept form. The negative 1/4 is the slope of a line, and the negative 2 would be the y-intercept where it crosses the y-axis if you were to graph it. Okay. We did kind of forget to mention here, now that we've got that solved, is there an association in the scatter plot that we just looked at? And the answer would be yes. It's positive, and the data kind of lines up on a line, so it would be positive and somewhat linear. Not tightly linear, perfectly linear, but somewhat linear. So positive and somewhat linear, right? So positive. Okay. So what are scatter plots in a line of best fit? Well, a straight line that is best represents the majority of the data in a scatter plot is a trend line. It helps us predict values that are not displayed on the plot or numbers that are way out beyond the scope of the graph, and it will show the trend. When we make a trend line like this, or a line of best fit as it's often called, we need to write it in a certain form, and the form we're going to use is y equals mx plus b. And that will be the equation of the line. When you do a line of best fit, you try to approximate the data as best you can, and we're going to demonstrate that in just a moment. But the line may pass through some of the points on the graph, or none, or it might pass through many of them. It just depends on the situation. So this is what we're talking about. If this is the data of temperature and the cost to heat your house or something like that, in this case it would be the cost to air condition your house. The warmer it gets, the more you'd have to spend to cool things down. So as you can see, the data kind of goes from left to right upwards. So you can actually make a little line here that kind of approximates the data, and you could use that line to predict future amounts. And yes, they would be approximations. Here's another one. This talks about the year and the average sea level in millimeters. And so as you can see, over time, sea level is going up. Now it looks like it's going up a lot, but these numbers are millimeters, so it's just actually kind of a small measurement, but still it's going up. So here's a line that kind of predicts that, and you could actually write a y-intercept to represent where it crosses over here. You could find the slope of that line and kind of predict where sea level is going over the next few years. Okay, if we look at these particular graphs, we might see some of these on Alex. Let's look at this first one, time watching TV versus the grade that you get. So which one of these lines looks like the best fit of the data? Well, of course, this last one does, because you can see the line goes down through the data, it has the right trend, and it's close to many of the points. So that's the idea of a good line of best fit. On this next one, the line goes up through some of the data. The line doesn't go through very well. It kind of cuts the data in half, but not in the right way. This line, on the other hand, cuts the data as well as we can expect in half, with about the same number of points above and below. So this is the best fit. And again, this is not an exact science, but it works. Okay, so when we get to a certain point, we're going to write an equation for these lines in slope-intercept form, and the way you draw the line is also helpful in that process as well. Okay, so here's the instructions on how to draw a line of best fit. First of all, you get a line tool and you draw a line. And what I like to do is I like to start down at the lower left-hand corner and say about where would this start. And you can adjust it as time goes on, but I'm going to come down here and one of the keys to this is when you start on the y-axis down here, try to pick a value that you know what it is. So I'm going to start right there. I need to back up just a moment. I didn't start going as soon as I picked my line and started. Okay, so you grab it, you put a dot on the left end and you come up through the data, especially in the case where I have this line tool. And you think, okay, that's pretty close. If you have an electronic line tool, you can kind of look at it and say, okay, I'm not sure if I like that. Maybe I need to go down a little bit better, something like that. So let's go with that one right there. So that approximates the data pretty good. The nice thing about this line of best fit is that it starts at 0 instead of about 5 where I was going to start it. And so that's kind of a way to help make the process of writing the equation easier. So first of all, we drew the line of best fit, and then we're gonna find two places where it crosses a known location. Well, one place would be right there, and then I'm looking up through there and trying to find another crosshair spot. It looks like right here it crosses a crosshair spot. So that would be a good one. So these 2 points are going to help us find the slope. So the slope, let's write that down. We know that the slope is the change in y. So we went up 10 and over 1 on this line. Now the others are similar. They might not be exact because again, this line of best fits are an approximation. So the slope is about 10. And then B, the place where we started our line of best fit, happens to be at 0. They won't all start at 0, but in this case it did. So if I write an equation that fits this data, I just go y equals slope times x plus the y-intercept, which is 0. So I can just drop the 0, and that's my equation of the line of best fit. And that's pretty close. All right, so there's my equation of the line. Now, I'm going to use this to predict how the distance I would travel in 10 hours. So in that case, I would just go y equals 10, and then x is the time traveled, so I'm going to put in 10 for x, and 10 times 10 would be 100. So according to our line of best fit and the equation that goes with it, we're going to go about 100 miles in 10 hours. All right. Now, when you first start doing these, you're going to have this urge to want to do it exactly right the first time, and it just takes a little bit of practice. So don't be too uptight about it. All right. So we've got to draw a line of best fit in this situation. So let's get our line tool. When I come up here, I'm going to try and pick a point over here that is identifiable, because if you just kind of pick a random point, you might not be able to find your y-intercept very clearly. So, I started going to the wrong tool. So I'm going to come up here about, okay, let's try 28 and see how that looks. If I come down through here, from 28, 32, it won't always work out quite that way, but that doesn't look too bad, does it? So that's a pretty decent looking line of best fit. So let's find out what our equation is. So first of all, we know that the y-intercept b, that we like to call it, is up there at 28. Now we need to find the slope, or m. And I noticed, as I come down through here looking for those crosshair places, that when I ended my line, I ended at 32, 0, and up here I was at 0, 28. So I really am going to use those two endpoints to help me with the slope. So the change in x over all of this time would be 32. The change in y would be from 28 down to 0, so it's going to be minus 28. And that's my slope, and I can simplify that. So you can use your calculator to simplify it. So you just do negative 28, fraction key 32, and that works out very nicely to be m equals negative 7/8. So now we write our equation, y equals negative 7/8 x, and then our y-intercept was plus 28. All right, now by using that equation from part A, we predict the time spent doing homework for a student who spends 12 hours watching TV. Well, 12 hours watching TV would be about here. So that intersects with our graph up here. So it's going to be somewhere a little above 16. But we can actually find a pretty good value by just plugging that in. So, and it says that we can use a decimal if necessary. So let's write it down. Y equals, and I'm going to use negative 7/8 at the moment. And so we're going to put in 12 hours there, and then add 28 at the end. So if I grab a calculator, and I just do negative 7/8, which I can do by just doing 7 divided by 8 equals, times that by 12, and then add 28. This calculator is not as good as the one that you use in class, so you can do that calculation a little easier. But my final answer there was y equals 17.5. So it's going to be 17.5 hours doing homework. If you spend 12 hours watching TV, then you're going to have enough time to spend 17.5 hours doing homework. So that's the idea of how to do those problems. Okay, I can use a line of best fit to predict the foot size of a person with a 20 centimeter hand. So if I look at the hand, you notice if I extend the line of best fit above my graph far enough, I can find out if a person has a 20 centimeter hand, that they're going to have a 33 centimeter foot size. So kind of crazy, huh? All right, so you can use lines of best fit to make predictions, and it's kind of easy how to do it. So predict the amount of money earned in 10 hours of work. So to do that, all you have to do is go up from 10 hours till you hit the line of best fit, and then go to the left till you hit the y-axis, and you're going to see that the predicted amount would be $72. Okay. All right, let's try this one. Predict the height of someone who weighs 150 kilograms. So we go to 150 kilograms, go up till we hit the line of best fit. That's going to be about right there. And so that lines up on the y-axis with the number between 100 and 110. So that's going to be 105 kilograms. Pretty nice. I like using these lines of best fit. Okay, so on Alex, you're going to see some problems like this as well. What is the predicted heating cost for a month with an average temperature of 0 degrees Fahrenheit? So if you go to your graph, okay, here's the average monthly temperature, and 0 is clear over here at the left side. So we got to come up here and predict where that line is going to cross right there. And it looks to me like it crosses right about 95. Now, when you put these answers in on Alex, they are pretty, they allow you to be off just a little bit and still give it to you as a correct answer. You don't have to be exact, but you got to be close. Okay, what is the predicted heating cost for a month with an average temperature of 25 degrees? Well, if we come over here, it's 25 degrees, so that's halfway between 25 and 30. So that's going to be about right there on our graph. So if we turn and go left, it's going to be somewhere between 60 and 70. So we're just going to go ahead and predict $65. Okay. For an increase of 1 degree Fahrenheit, what is the predicted decrease in monthly heating costs? Which sounds kind of complicated, but all you have to do is look in front of X and find the slope. That's the predicted change for 1 hour, or for 1 degree Fahrenheit in the predicted, not 1 hour, I was trying to say time, but it's actually change in temperature of 1 degree. That's how much it's going to cost to heat your house in this case, or how much less it would cost. So the amount would be negative 1.23. And in some cases, if it, depending on the wording, you might just need to type in the number. If it already says decrease, it's going to assume that you mean negative. Okay, so that's the kind of things we're going to be doing today. I really like this lesson, so I hope you'll like it too. Number 65, line of best fit on Alex. Good luck.